Okay, it has started. So this is especially for Darren and Chris. Yeah.
Can we say hi?
Yeah, go ahead.
Hi. Where's Chris? Hi, Chris.
Okay, we are on page 50 to 54 of the Electricity 1 booklet. So we should... He's already stuffed it up. We should be there. Yeah? So there's a graph. Question 1. I'm going to go through question 1 with you, and then you're going to have a go at all the other questions. So we have an IV graph for 2 electronic components. We don't know what components they are, but I think we can guess what X is. Looks like a resistor. Yeah, and Y, not really any idea what Y is, but we know it's non-ohmic. That doesn't really matter. What we're interested in is the fact that it's connected in series. What might be useful, I'll do this at the end of this question, it might be useful at this stage to draw that circuit, because that's not a circuit, that's a graph. But I won't draw the circuit just yet. I'll see if you can think this through without drawing the circuit. If it's in series and there's 5 milliamps of current, what's the current flowing through Y? So I'm going to ask Kevin straight off if he knows anything about current in series.
It's the same.
So he says the current in series is the same, and he's spot on. If it's the same, and we're told that the current flowing through X is 5, so this is X and it's 5. Yeah, so at that point we should get 5 milliamps. But Kevin says the current in series is the same. That means that Y should also be 5. Does that make sense? So that's got to be 5 as well, just there. Because in series, the current is the same. So current flowing through Y is also 5 milliamps. So far, so good. The potential difference across X and Y. David has just let rip with an inaudible yawn. So he's going to tell me the potential difference in series. What can you tell me about that? The voltage drop in series.
Current stays the same.
Correct.
Resistance in series just adds.
Yep. ATQ. Answer the question. What is it about potential difference in a series circuit? Antonio's going to answer.
Series circuit, the voltage adds.
Yeah, the voltage adds up. It's shared. Yeah. So the potential difference is shared in series. So if we look at the graph and we have 2 currents that are the same because they're in series, the 2 voltages must be different and they must add up. So all we do is read off the voltages off the graph. For X, the voltage is 2.5. For Y, the voltage is 3.8. Excuse me. There we go. So far, so good. We can use the graph to tell us the current through each component and the voltage across each component. Yes? We don't need a circuit. We just use the graph. So far, so good. Okay, next. Let's work out the resistances. You know that V equals IR. And because Antonio's mathematics is brilliant and he can manipulate F equals K, Q1, Q2 over R squared, he can also manipulate V equals IR to find R. Yep. And all he does then is put in the voltage for Rx. Voltage is 2.5. And he's not going to make this mistake. How many of you made this mistake in the test?
What mistake?
Well, it's not 5. The current is not 5. the current is 5 milliamps. So you have to have 10 to the minus 3. Were there any occasions in the test where you had to muck around with units?
Oh,
Yes,
that
but
little
the
Plenty.
graph, the graph.
Yeah, plenty of times.
I think that comes up by
I didn't
10 to the
think
power of 3 negative.
So RY is the same thing. We've got a voltage at 3.8, but we're careful about units. That's why we did the data analysis booklet. We're careful about units, and we make sure it's milliamps. So our two resistances are 500 ohms and 760 ohms. I can go with Hayden Korn, who's going to tell me in series what happens to the resistance. It adds. Simple. So the total resistance is just going to be adding up the resistors, which is 500 plus 760, 1,260. So we write that in kilo ohms because the question says in kilo ohms. There we go. So that's in series, yeah? We're going to analyse this circuit, or this graph, the same way, but in parallel. Kevin was a series genius, and he's going to tell me what happens in parallel.
Parallel, the current is different and the voltage stays the same.
So in parallel, the voltage stays the same. So whatever voltage we get for X and Y is going to be the same. So you can imagine we're going to have a vertical line somewhere because the voltage will be the same, but the current will add up. So we'll have two different currents. PD is the same in parallel and current is shared. Let's go concepts. Stephanie, where does the idea that PD is the same and current is shared come from? What two big ideas that we covered tells us that?
Oh, those laws?
Those laws, correct.
Yeah.
Which two laws?
The one that voltage coming into an intersection equals voltage coming out.
Current coming in.
Current and the
And the voltage is shared.
Yeah.
But who was this named after?
Curve.
Kirchhoff. So this idea is basically an extension of Kirchhoff's laws. And the test that you just did would have been really straightforward if you understood Kirchhoff's laws. Okay, so there's the current. We're told that it's 5 milliamps. X has a current of 5, but Y can't have a current of 5 because it's in parallel. But we do know that X will have a voltage of 2.5, but that means Y also has a voltage of 2.5. They both have the same PD. So now you go, well, how the hell do I find out the current of Y? If the PD is the same, then the current of Y is going to be here. David got it right. It's going to be 2. So in parallel, we look at the graphs differently. So the current in Y is 2 milliamps. Let's have a look at this in a little bit of a summary. And so this is stuff that's not in your booklet. This is just me summarising this whole idea. In series, we kind of look horizontally this way because the current stays the same and the voltages are different. Now I've drawn a circuit. So maybe the circuit helps. So if you're confronted with these questions and you're a little bit stuck, it might be an idea to draw the circuit. You can just draw rectangles regardless of what the device is. So they're in series and you know that the current is the same. And so in series, the current goes around the circuit and it's always the same, which means the voltages for X and Y have to add up to the voltage supplied by the battery. So this is how you think about graphs like this in series. Current the same, voltage different. In parallel, we think about it differently. In parallel, the voltage is the same, but the two currents are different. Maybe a diagram will help. So it's a parallel diagram. And you can see that the voltages are the same. Kirchhoff's law. The currents are different. You've got one going through X, one going through Y, and they both add up together to make the current supplied by the battery would be 7 milliamps. So those last two things, the supply of the battery, the total current, weren't asked in this question, but they're sorts of things that you might be asked. Given that there's 5 milliamps and this is the graph, what's the total current if it's in parallel? Or you might get questions where you're given the supply voltage, this, and the current, work out the voltage across Y. And you should be able to do that. Okay, so we are going to have a go.